Here is the chapter 3C, Kinetics of Charge Transfer Controlled Systems. CT stands for charge transfer in the slide of today. Until now, in the previous chapter 3A and 3B, we have focused on the mass transfer controlled systems in terms of kinetics. But right now, we are going to the charge transfer controlled systems. In the mass transfer controlled systems, the rate capability of charge transfer is much faster than the rate capability or kinetic capability of mass transfer. So we have assumed that the overall kinetics is totally determined by the mass transfer. Also, we have focused on the diffusion process, dominantly determining the mass transfer process. So we have used the fixed first law and fixed second law as the diffusion equations to obtain the kinetics about the mass transfer controlled systems. In this chapter, we are focusing on the charge transfer controlled systems rather than the mass transfer controlled systems. Here is the content for this chapter 3C. At the very first time, I will try to compare between the charge transfer and mass transfer controlled systems. Butler-Balmer equation is the most representative equation for describing the kinetics of charge transfer controlled systems. The starting point for deriving the Butler-Balmer equations is reaction coordinate diagrams. After understanding the reaction coordinate diagrams, when we have applied the potential into the electrochemical system, then we will get the Butler-Balmer equation of version 1. This version 1 equation having the standard rate constant in centimeter per second with the formal potential. Also, this equation includes a parameter which is the transfer coefficient alpha. Then I will test the version 1 of Butler-Balmer equation in terms of its feasibility. Does Butler-Balmer equation satisfy Nernst equation? The answer should be yes. Then let's go to the Butler-Balmer version 2, having exchange current I0 instead of the standard rate constant K0. Then graphical representation of Butler-Balmer version 2, and then I'll introduce some special cases of those Butler-Balmer equations. Also, please refer to the chapter 3 of Barth and Faulkner book. Okay, here is the comparison of kinetic capability between charge transfer and mass transfer. Of course, we are thinking of this reaction, oxygen plus and with electron, which is going to the reduced species. The kinetic capability of charge transfer process without limitation of its computative mass transfer process will be compared with the kinetic capability of mass transfer process without limitation of its computative charge transfer process. And then we can determine whether your system is mass transfer limited or charge transfer limited. Let me think about the mass transfer limited system. You have already learned about that yet. In this case, charge transfer is much faster than the mass transfer in terms of kinetic capability. Therefore, you have fast charge transfer reactions. I'd like to emphasize the meaning of fast, which is equal to reversible, as you know, or facile, moreover Nernstian, because surface concentrations are determined by Nernst equation. What does it mean? I'd like to change the sentence in this way. Surface concentrations are determined by thermodynamics because the kinetics of the reaction, charge transfer reaction, is really fast. So the surface situation is determined by thermodynamics instead of kinetics. Therefore, again, mass transfer will determine the overall kinetics. So we can focus on the surface diffusion. Surface diffusion will determine the current, or that is to say, Fick's first law will determine the current in the mass transfer limited system. Let me check those equations. Current per number of electron transferred, Faraday constant with electrode area, can be described by mole flux at the surface, because mass transfer determines the overall kinetics. So again, current is determined by mole flux. If your diffusion process is dominant over migration or convection or blah blah, then this surface mole flux or surface mole flux or mass transfer is described by the surface diffusion. So again, I can say surface diffusion will determine the current in the mass transfer limited system. Then let's go to the charge transfer limited system, which is the main topic of this chapter. The kinetic capability of charge transfer is much slower than the kinetic capability of mass transfer. So it means we have a slow charge transfer reactions, where we have a slow Faradaic reactions, which would be oxidation or sometimes reaction. Surface concentrations are determined by kinetics instead of thermodynamics. Again, surface concentrations are determined by reaction rate equation instead of Nernst equation in the charge transfer limited systems. So the current cannot be described by mole flux anymore. Instead of mole flux, we should think about the reaction rate equation. Again, current is determined by reaction rate equation, or surface reaction, or in other words, mass action law, instead of surface diffusion or Fick's first law. Here is the reaction rate description. Maybe you are very accustomed to the mass action law. What is that? The overall reaction rate can be described by the rate of the forward reaction minus rate of the backward reaction. Each reaction rate can be described by the product of the rate constant with the surface concentration of reactants. For the forward reactions, the reactant is oxidized species because this direction is the forward reaction. So the surface concentration of oxidized species is used for the forward reaction rate. On the other hand, for the backward reaction, the reduced species is reactant. Therefore, the backward reaction rate is the backward reaction rate constant with the concentration of reduced species at the surface. It is big difference, you know. Current is the mole flux versus current is the reaction rate. There is a big difference between the charge transfer limited system and mass transfer limited system. So in this chapter, the starting point is these equations. From now on, I will try to derive the Butler-Balmer equations. Of course, we are thinking about these electrochemical reactions. Oxidized species is going to the reduced species or vice versa, with forward rate constant or backward rate constant. The first thing for deriving the Butler-Balmer equation is to understand the reaction coordinate diagram. The reaction coordinate diagram is free energy diagram as the y-axis along reaction progress x-axis. So let me check the free energy curves for the reactant and product. We have two free energy curves here for the reaction coordinate diagrams, and the first curve is responsible for the reactant, including oxidized species with electrons. The other curve is responsible for the reactant or the product or reduced species. So this is the free energy for the initial reactant, and this is the free energy of the product. Between them, you can find the maximized free energy. This is the energy for the intermediate or transient state between the reactant and product. Maybe, as you know, this barrier or the height or this barrier is related to the activation energy. Those two black curves are obtained before you have an applied potential. So let me say the applied potential is 0 right now. And let me check three parameters. The first two parameters, which are the activation energy, are responsible for the kinetics. And the third one is about the thermodynamics. This is the activation energy, delta G star, for the cathodic process of the forward reaction. In this reaction, forward reaction is the cathodic process or reduction reaction. At the initial state, O indicates the state before you have an applied potential into the system. So delta G star OC means the activation energy of the cathodic process at the initial state before the applied potential. How about the activation energy for the backward reaction? Here, activation energy of anodic process for A at the initial state for the O here. How about third one? This is the free energy change between the product, here reduced species, and reactant, here oxidized species with electrons. So let me say, without any applied potential into the system, the Gibbs free energy change is the NFE0. I mean standard Gibbs free energy or standard reduction potential before you have an applied potential into the system. That is the situation before you have an applied potential. Then let me apply a potential into the system. The potential value is here indicated by E. So on applied potential, E is applied into the system. Then something changes. You know, you can find the electrons in the reactant, not in the product. So by controlling the potential, you can control the free energy curve of the reactants because you have the electrons in the reactant size. So this black curve is shifted downward into the blue dashed line because you have an applied potential, the value of which is positive value. So when you have a positive potential into the system, then your free energy diagram of electrons, actually reactants, is going down. Of course, if you have a negative applied potential, then this black curve is going upward. But let me say, in this situation, I have applied positive potential into the system. So this dashed line, blue dashed line, is found below the black curve. Then let me check the activation energy. So before applied potential situation, I mean before you have an applied potential, then you have this activation energy. But right now, the activation is changed from here to there. Then let me define the activation energy as the delta G star without O of the cathodic process. So this value is going to the other value. Looks similar, but something changes. The change is found clear when you look at the backward reaction, of course, in this case, oxidation process. So at the initial state, before you have an applied potential into the system, you have the length, this length, about the activation energy for the anodic process. However, when you applied a potential into the system, this delta G star O anodic process is going to delta G star just the anodic process without O. Of course, the activation energy decreases after you have applied a positive potential into the system. So something changes, clearly found. Then one more things. In this case, the change, the difference of free energy between the black line and the blue dashed line is delta G, which is determined by your applied potential, NFE. The more important thing is here. Of course, still we have the same distance. Let me say distance is the same as that of this, right? It should be. And let me divide this length, or this line, with two terms. The second terms, let me define alpha NFE. And then you should say the other length is 1 minus alpha NFE, because the summation of those two lengths should be NFE. Then alpha is so-called transfer coefficient. You will learn about that later. Then right now we have this kind of geometry in this reaction coordinate diagram. Here is the reaction coordinate diagram for the oxidation reduction processes we have just drawn in the previous slide. Based on these shapes and parameters in these reaction coordinate diagrams, then I'd like to derive the equation. Of course, the starting point of the equation should be mass action law. Current per NFA should be described by the reaction rate, like rate constant for the forward reaction with the surface concentration of oxidized species minus backward rate constant with the surface concentration of reduced species. Then I'd like to focus on the reaction rate constant because potential would affect the reaction rate constant, doesn't affect the concentration term. So this column is about the forward reaction rate constant, which will be found as the function of the potential. And in the other column you can find the backward rate constant. So let me start from the final state description. Here, final state indicates the state after we have applied a potential into the system. So the blue cases. So forward reaction rate constant can be described by Arrhenius equation. So it means free exponential term for the forward reaction with the exponential function of minus activation energy, this one, per RT. In the same way, backward rate constant can be described by the Arrhenius equations. Of course, in this case, you should use another activation energy for the backward reaction at final state after you have applied the potential into the system. Then, as the second step, I'd like to correlate the final state with the initial state. So let me think about the length from here to there. Then, from the viewpoint of final state, this length is the delta G C star plus 1 minus alpha and Fe. From the viewpoint of the initial state, here initial state indicates the state before you have applied the potential into the system. So from the viewpoint of the initial state, this length is the summation of delta G O C star here plus NFE. Then by reshuffling these equations, then finally we can conclude that the final activation energy is equal to the initial value plus alpha NFE. Again, final activation energy is the summation of the initial value plus alpha NFE. Okay, that's for the forward reaction. How about the backward reaction? For the backward reaction, let me think about the length from here to there. Then, from the viewpoint of final state, delta G star anodic process plus 1 minus alpha NFE is equal to the delta G O star A here. Then finally we could obtain the final is equal to initial minus 1 minus alpha NFE. Then let me use this relationship. So I'd like to describe the forward reaction rate constant with initial state parameters. So we have this relationship and this relationship, and then let me replace the activation energy for final state to the activation energy for the initial state. So put there, or this one is going to there. Then finally we have obtained this one. So here the rate constant can be described by the initial activation energy with the potential. Initial activation energy with the potential. You can find the small f instead of large f. For simplicity, I have replaced the Faraday constant per ideal gas constant with temperature with the small f. Anyway, right now, we could describe the rate constant for forward and backward directions in terms of the initial activation energy with the potential. So finally, we can find the potential dependent term. Actually, we should focus on the potential dependent term. That is the electrochemistry. We can control the potential. Something changes with the potential. So, I'd like to get together all of the potential independent terms. In this case, pre-exponential term with the exponential term, which is potential independent. So let me say this value as the kf0. Also, in the other column, backward direction, then this one is going to the kb0. So right now, the expression for the rate constant was very simplified. Reaction rate can be described by some coefficient with exponential function of the potential. And okay, that's it. Then, okay, so right now we have the mass action law. So we could describe the current with some surface concentration and potential dependent rate constant Kf and Kb. The potential dependency of both the rate constant are here, like Kf can be described by exponential function of potential, and also backward rate constant is also described by exponential of potential. So these equations, I mean again the mass action law with the potential dependent rate constant, should be working with any conditions. I mean at any concentrations and any potentials, these equations should be right. So let me think about very specific conditions or cases. Then at that specific cases, everything should be right for the equation. So at equilibrium with a bulk solution at CO star, I mean the concentration of oxidized species as the bulk concentration and equal to bulk concentration of reduced species. I means equimolar concentration case for the oxidized species and reduced species plus equilibrium. At these conditions, my equations should be working, right? So what does it mean? Equilibrium plus shear star equal to shear star. Let me start with the equilibrium. At equilibrium, current should be 0 because that is the equilibrium. What is the equilibrium? For the reaction rate should be equal to the backward reaction rate. This one should be the same as this one. So current should be 0. How about the potential? Equilibrium potential should satisfy the non-state equation. So equilibrium is equal to E0 prime minus RT and per NF ln bulk concentration of reduced species per the bulk concentration of oxidized species. I should emphasize this concentration is the bulk concentration value at equilibrium. Also, we could use the equimolar concentration term. So let me put the values about the bulk concentration into here. Shear star per shear star is going to 1, so the log term is going to 0. Then finally, at this specific situation, E is equal to E0 prime, right? because E equilibrium is E0 prime. Then let me use these conditions for the mass action law with the potential dependent reaction rate constant. So mass action law here, and current is going to 0 at this specific situation. Also, the Kf values should be at the formal potential. Also, the same thing for the backward rate constant, and more thing, and then surface concentration of oxidized species and reduced species are going to the bulk concentration at equilibrium. One more thing, shear star is equal to zero star. So the forward rate constant at formal potential, or by using this equation, this one should be equal to that one for the backward reaction. Then let me define those two description for the forward reaction and backward reaction as the K0, which is called standard rate constant. Again, standard rate constant. Then right now, Kf0 can be described by K0 with exponential function of plus alpha and f E0 prime, because I'd like to shift this one into the right side of the equation. Or Kb0 can be described by the same standard rate constant with the exponential function of minus 1 minus alpha and f formal potential. Then let me put here and here. Then finally we could obtain this equation. Forward reaction rate constant and also backward reaction rate constant can be described by the function of the potential difference with respect to the formal potential. And then also you can find the two parameters, K0 and alpha, also K0 and alpha. Okay, then let me put this description to the mass action law. Then Kf is replaced by K0 with the exponential function of potential, and in the same way Kb is replaced by this equation. Then finally we obtain this equation, which is called Butler-Balmer equation version 1. Current is equal to NFA, always NFA, it should be involved, with K0. You can find the K0 on both rate constant, so you can get the K0 out of the parentheses. And still we have surface concentration here. For cathodic process, your potential dependent term is read as exponential of minus alpha NF E minus E0 prime. For the backward reaction, the potential dependent term is read as exponential function of 1 minus alpha NF E minus E0 prime formal potential. So you can find alpha for the forward reaction or cathodic process, and 1 minus alpha is found for the anodic process. The sign are different. Here is the minus, here is the plus. So let me try to understand the Butler-Balmer equation. I have drawn some curves about the Butler-Balmer equations. The overall current can be described by the current for the forward reaction minus current for the backward reaction. I mean, the overall current is the summation of the cathodic current and anodic current. This simulation is obtained by those simple values and the number of electrons transferred was assumed to be 1. Faraday constant, of course, 96500, and the standard rate constant was assumed to be 10 to the minus 6 centimeter per second. And the concentration of oxidized species at the surface is 1 mole per cubic centimeter. And also concentration of reduced species at the surface is 1 mole cubic centimeter. So equimolar concentrations for oxidized species and reduced species. Alpha, so-called transfer coefficient here, is 0.5. Temperature 25 Celsius degree room temperature. R, ideal gas constant, and small f was redefined as the F per R per T or something like that. And the total current J indicates actually current density, ampere per centimeter square. The overall current is the summation of cathodic current plus anodic current, and cathodic current is the first part of the Butler-Balmer equation, and second current term is the second part of the Butler-Balmer equation involving the minus signs here. So the summation of those cathodic and anodic processes is going to the overall current here. Okay, then let me think about the graph. X-axis is the potential with respect to the former potential. So 0 means former potential. Y-axis is the current density. So J can be defined as current per A. Then we have the green curves for the overall current. And this overall current can be split into two curves. The first curve is about the cathodic current, and the other thing is the anodic current. Black one for the first term of the Butler-Balmer, and the red one is for the second term of Butler-Balmer. So let me scan the potential from the very positive value to the negative value. And then in that case, the cathodic current is exponentially increased. However, at the same time, the anodic current is exponentially decreasing. So at the high negative potential, you could find the cathodic current, the sign of which is positive. And then let me return the potential from the negative potential into the positive potential. So the cathodic current decreases along the potential scan, and the anodic current would increase exponentially. So finally, at the very positive potentials, you could have the oxidation, of course. That is the Butler-Balmer equations for the charge transfer limited systems. So I have said Butler-Balmer equation have two parameters. The first one is K0 here, and the second one is alpha. So you should understand the physical meaning of those two important parameters. Here, the first one, which is the standard rate constant K0. The unit of the standard rate constant is centimeter per second. This is the unit of velocity word. So you can understand this is a measure of the electron transfer velocity or speed. So K0, again, K0 is a measure of the kinetic facility of a redox couple, right? And large K0 indicates a very facile or fast or reversible or Nernstian charge transfer reaction. Of course, in this case, the surface compositions are determined by Nernst equation, so If you have the very large K0 reaction, then maybe you could assume that your system is the mass transfer limited system instead of charge transfer limited system. The surface compositions are determined by Nernst equation, of course, and this fast reaction is associated with particularly very simple electron transfer, usually with only one electron and resolvation. Therefore, no significant change in the molecular structure is involved with the large K0 reaction. When we are saying our electrochemical reaction is very fast, it means K0 is in the range of 10 to the 0 to 10 to the 1 centimeter per second. Okay, several centimeter per second, it means it is very fast. However, let me calculate this value into the unit of meter per hour. 10 centimeter per second means 360 meter per hour. You know, this speed is slower than the speed of our working. However, just several hundred meter per hour is very meaningful for the electrochemistry. So again, 1 to 10 centimeter per second is the value which can be considered to be very fast in terms of charge transfer kinetics. Here are two examples. I'm not sure of this kind of reaction you have accustomed to. Amalgam formation. Sodium plus is getting the electron to sodium, but at the same time mercury is involved in this reaction. This mercury alloy is called amalgam. In this reaction is very fast. The other thing is anthracene chemistry. Anthracene looks like this one, and this is this is oxidized very fast or reduced. Let's go to the other side of the small K0 world. Small standard rate constant indicates a sluggish or slow charge transfer reaction, of course, involving complicated reactions with significant molecular arrangement during the electron transfer. Or sometimes multi-step mechanisms are involved for the slow electrochemical reactions. Usually much less than 1, like 10 to the minus 3 centimeter per second or something like that. Here is the hydrogen evolution reactions. 2 proton getting 2 electron going to hydrogen gas evolved. Looks very simple. However, this reaction has a multiple step mechanism. So the rate constant, the standard rate constant is very small. So we need to have some electrocatalyst like a platinum. So again, I'd like to emphasize the meaning of standard rate constant K0, which is a measure of kinetic facility or kinetic velocity or speed of a redox couple. Here is the second parameter of Butler-Balmer equation. That is the transfer coefficient alpha. Sometimes it is called symmetry factor. Here is the Butler-Balmer equation, and you can find the alpha in the exponential function of the potential here, and for the cathodic process, and also another exponential function of potential for the anodic process. Here is alpha, and here is 1 minus alpha. The transfer coefficient alpha is a measure of the symmetry of the energy barrier. Let me magnify a portion of the reaction coordinate diagram around the energy barrier. Here is a single product line, and we have two different reactant lines. The first one is obtained at potential is equal to 0, and the other reactant lines are coming from the potential equal to some value, like applied potential is equal to E. Then let me think about this line. From the intersection point of the product and reactant curves at E equal to 0, and the point on the reactant curve at E is equal to E at the same reaction progress. This line can be split into two sections. The length of the first section is 1 minus alpha NFE, and the lower part of the line is the alpha NFE in its length. Of course, the summation of the lengths should be NFE. Also, I'd like to define the angles for this line as theta, and the other angle is phi for the product line. The angle over here should be theta because it is the opposite angle of theta here. So right now we have theta, theta, phi, and also one more thing. So this line, the length of this line is x here. Then with this geometry and related parameters or symbols, we could calculate the alpha value in terms of theta and phi. Tangent theta here, tangent theta is equal to alpha NFE per x. Tangent phi, this one, is 1 minus alpha NFE per x. By combining those two equations, alpha can be described by tangent theta over the summation of tangent theta plus tangent phi. If the theta is equal to phi, alpha is going to 1 over 2 or 0.5. At alpha equal to 0.5, the product curve, this one, is a mirror image of the reactant curve over the y-axis because theta is equal to phi. In other words, the energy barrier is symmetric between the reactant curves and the product curves. Again, alpha is equal to 0.5. We should obtain the symmetric energy barrier. That is to say, the slope of the left heel of the energy barrier mountain is equal to the slope of the right heel of the energy barrier mountain. So this mountain looks symmetric at alpha equal to 0.5. And then let me modulate the value of alpha into the value less than 0.5. What happens for the reaction coordinate diagram? Here is the product line, and the product line where the right heel of the energy barrier mountain becomes steeper at alpha less than 0.5. Or on the other hand, if the values of alpha is going to the values larger than 0.5, the product curve becomes gentler than the case at alpha equal to 0.5. What is the physical meaning of steeper and gentler slope of the right hill of the energy barrier mountain or reactant curves? The distance of reaction progress along x-axis between the initial state and the intermediate state determining the activation energy could be used as a measure of how many intermediates are involved in the reaction. Let me compare those two product curves. The dashed blue line was obtained from the alpha equal to 0.5, and the other gentler product curves is obtained at alpha larger than 0.5. At alpha equal to 0.5, the distance between the initial state and the intermediate state is shorter. At alpha larger than 0.5, for the gentler slope case, the distance between the initial state to the intermediate state is longer. Therefore, longer distance indicates we should experience more intermediates before going to the top of the mountain. It means slower kinetics. On the other hand, if you have the shorter distance between the initial state and the intermediate state, it means we have the smaller number of the intermediates before going to the top of the mountain. Therefore, the shorter distance indicates the faster kinetics. So let me summarize the interpretation for this geometry. The steeper, the faster, and the gentler, the slower. Based on the understanding about the reaction coordinate diagram, let me try to expect the current potential curves based on the Butler-Balmer equations. Here I have plotted Butler-Balmer equations with three different values of alpha: 0.5, then 0.2, and finally 0.8. At alpha equal to 0.5, we have a symmetric shape of the Butler-Balmer curves. The cathodic curve is very similar to the anodic curve. That is to say, the anodic curve is a mirror image of the cathodic curve over the origin. Let me go to the 0.2 case for alpha value. For this situation, that is to say alpha is less than 0.5, we have the steeper right heel of the energy barrier and the gentler left heel of the energy barrier. The steeper right heel indicates faster backward reaction from the right side to the left side. That is to say, faster oxidation, because we are thinking about the electrochemistry of oxidized species plus electron is going to the reduced species. It means higher anodic current is obtained at alpha equal to 0.2. The gentler left here of the energy barrier when compared with the steeper right here, which indicates slower fold reaction from the left to the right. That is to say, slower reduction. Then we would obtain lower cathodic current. Let me check this situation at this current versus potential curve. At a fixed potential, we would obtain the lower cathodic current for 0.2 when compared with the case at 0.5. Let me go to the anodic process. At a fixed potential, we will have higher current for 0.2 when compared with the 0.5. So in this case, the anodic process is favored at alpha is smaller than 0.5. Let's go to the other value of alpha, which is the 0.8. For this case, in other words, when alpha is larger than 0.5, we would obtain the gentler right here of the energy barrier, and relatively the steeper left here of the energy barrier. The gentler right here indicates slower backward reaction from the right to the left. That is to say, slower oxidation, which results in lower anodic current. Also, at the same time, the steeper left here of the energy barrier indicates faster forward reaction from the left to the right in this reaction coordinate diagram. That is to say, fast reduction would be obtained, resulting in higher cathodic current. Let me check it. In the cathodic process, at a fixed potential, you will have the highest cathodic current for 0.8 when compared with 0.5 or 0.2 here. In the anodic region, 0.8 value for alpha would provide the smallest values of the current when compared with the cases of 0.5 and 0.2. So we could expect the current versus potential curves from the reaction coordinate diagrams. As a summary, higher alpha from here to there favors cathodic process. Let me emphasize it again. Higher alpha values favors cathodic process. We have a single equation for the thermodynamics in the electrochemistry world. What is that? That is the Nernst equation. Butler-Balmer equation is the kinetic equation, and any kinetic equations should satisfy the thermodynamics. So, at equilibrium, the Butler-Balmer equation should be converted to the Nernst equation. Let me check it. Here is the Butler-Balmer equation version 1. Current is equal to NFA standard rate constant with the concentration of oxidized species at surface with some exponential function of the potential having alpha and f minus surface concentration of reduced species exponential function of 1 minus alpha and f e minus e0 prime. At equilibrium, current should be 0 and the surface concentration should be bulk concentration for oxidized species and reduced species. Let me put this equilibrium condition into the Butler-Balmer equation. Then current should be 0, so this term is equal to this term, like that, and the potential should be equilibrium potential, and surface concentration is converted to the bulk concentration. By reshuffling this equation from here to here, then finally we could obtain the nonce equation, which is equilibrium potential is formal potential minus RT and F, the log of bulk concentration of reduced species per bulk concentration of oxidized species. Right now we have the Butler-Balmer equation version 1 on our hand. Butler-Balmer equation have two parameters. One is K0, standard rate constant, and the other thing is the alpha. Also, Butler-Balmer equation version 1 is the function of potential, and the potential was described by the potential difference with respect to the formal potential. Let me change this version 1 into Butler-Balmer equation version 2. Again, at equilibrium, cathode current should be the same as the anode current. And surface concentration is going to bulk concentration. Here is the cathodic current at equilibrium. Look at that. Potential is going to equilibrium potential with the bulk concentration. And this is the anodic current. Cathodic current and anodic current should be the same at equilibrium. Then this current can be defined as the exchange current. Here I0. So again, the cathodic current at equilibrium should be the same as the anodic current at equilibrium. Also, we could define the equilibrium current for each process as the exchange current. Let me divide this equation by the other equation. Then you could obtain CO star per CR star equal to the exponential NF equilibrium potential minus formal potential. Then let me put some alpha, minus alpha value here. Then this term is the same as this term. Therefore, I could replace this term by the concentration ratio to the minus alpha term. Then, finally, the I0 is redefined as NFA, K0, CO star 1 minus alpha, and CR star to the alpha. That is to say, the exchange current is proportional to the standard rate constant. So, if you have a higher standard rate constant, then you could expect higher exchange current at equilibrium. You should recognize that the exchange current I0 is an extensive property, or is extensive variable. That is to say, the exchange current is proportional to the electrode area. It means if you use the larger surface area electrode, then you could obtain the higher exchange current. Also, the exchange current depends on the the bulk concentration of oxidized species and reduced species you have introduced into the system. So, the size of your system, depending on the concentration, depending on the electrode area, would determine the intensity of exchange current. However, K0 is intensive property, which is independent of concentration or electrode area. So usually the standard rate constant is used as the intrinsic property of your electrochemical reaction. However, the exchange current have the information about your system size. Anyway, right now we have defined the exchange current, and exchange current can be described by this one, the other one, the last one. Then let me divide the Butler-Balmer version 1 by exchange current. I per I0 here is equal to the first term is divided by this one, because it is the exchange current. Then which is going to the concentration ratio between surface to the bulk with exponential minus alpha and f, then eta. Eta is the potential with respect to the equilibrium potential instead of formal potential, which is called overpotential. Also, in the same way, the second term is divided by this equation. Then you could obtain the similar function, like surface concentration to bulk concentration for the reduced species, and exponential function of 1 minus alpha and f over potential. So, different from the Butler-Balmer version 1, Butler-Balmer version 2 equation have the exchange current as its parameter plus alpha as its parameter. So I mean the K0 is going to exchange current for the version 2. Also, potential difference is described with respect to the equilibrium potential instead of formal potential. That is the Butler-Balmer equation version 2. So let me think about the current versus potential curve for the Butler-Balmer equation version 2. As shown in the Butler-Balmer equation version 1, we have 3 graphs here. The green one is the overall current. The black one is the cathodic current, and red one is anodic current. Of course, the overall current is obtained by summing the cathodic and anodic currents. Let me magnify the region at the overpotential equal to 0, or the equilibrium potential. You know, x-axis is the overpotential, so 0 overpotential indicates the equilibrium potential. Then here magnified version around the equilibrium potential. We should have the zero value of current at equilibrium potential, of course. We could obtain this zero value because each cathodic and anodic current should be the same with the opposite sign in front of the current. The value of the current at equilibrium for each process is the exchange current. That is to say, the cathodic current is I0 and anodic current is minus I0. Therefore, at equilibrium, we would have zero value of current. So this is the exchange current. Let me change the current value of exchange current. The same current versus overpotential curve, and the black curve is obtained at exchange current equal to 10 to the minus 5 ampere, then 10 to the minus 6, then 10 to the minus 9. At the highest value of exchange current, you could obtain the highest value of current for the range of the potential. And then 10 to the minus 6. So at the same potential, this curve shows the smaller values of current. And moreover, at the 10 to the 9 ampere case for the exchange current, we have very small values at around the equilibrium potential. So this is the overpotential from the y-axis to the current curve against the overpotential. Then we could say with smaller values of exchange current, we can observe the series overpotential. However, in the case of the very large value of the exchange current, it looks almost vertical line. If you decrease the exchange current from some value to 0, then maybe you could not have any current over the all of the potential range. Right now, we have the Butler-Balmer equation version 2 on our hand. Then let me think about some special cases for simplifying the Butler-Balmer equations. Here is the case A, no mass transfer problem. That is to say, we have a purely charge transfer limited systems. In this case, the surface concentration of oxidized species and reduced species are going to the bulk concentration because our mass transfer is really fast. Then we could remove the concentration term in front of each exponential function of potential. So what I have is right now current is proportional to the exchange current with the exponential function of potential. Exponential minus alpha NF eta minus exponential 1 minus alpha NF eta. We have a cathodic process and anodic process simultaneously. This more simplified equation is generally known as Butler-Balmer equation. Let's go to the case B at small overpotential. Here is the current potential curve based on the Butler-Balmer equations. Let me focus on the potential range around the equilibrium potential. I mean the range of small overpotential. When we magnify this region, then we could recognize that the current is linearly related to the potential. Let me get some equations about that. I'm saying about the small overpotential or around the equilibrium potential. So the exponential function of this one and that one could be linearized. We'll use the Taylor expansion. If you have a very small x values, the exponential function of x is going to 1 plus x minus 1 over 2 x squared plus another polynomial terms. Because we have small values x, so we could kill the second order term, third order term, and also higher order terms. So I can say the exponential function of x is equal to 1 plus x. Then let me apply this relation. So we have here is the exponential function. Then this is going to 1 plus minus alpha nf eta here. Also, in the second term, here is the exponential function of 1 minus alpha nf eta is going to 1 plus 1 minus alpha nf eta here. Then it's going to minus exchange current with the number of electron transfer. Then small f indicates f per RT with overpotential. That is to say, current is just proportional to eta. It is very similar to Ohm's law, and we have confirmed this kind of linear relationship is obtained at small overpotential range. So I'd like to say this region is linear region around the equilibrium potential. I have said this linear relationship can be called by the Ohm's law. So from the slope we could define the resistance. That is the charge transfer resistance is equal to overpotential per current by definition of resistance. And by using this linear relationship, charge transfer resistance is equal to 1 over NF exchange current. That is to say, the slope of the current potential curve, then we could calculate the resistance of charge transfer. And then from this value, we could calculate the product of exchange current with the number of electron transfer. If we know the value about the number of electron transferred, then finally we could get the exchange current. From the exchange current value, we could obtain the value of the standard rate constant K0 by using previously presented equation. So finally, we could estimate the standard rate constant, which is a measure of kinetic facility. Here is the mass transfer resistance, which can be defined in the similar way to the charge transfer resistance. Mass transfer resistance is equal to 1 over NF limiting current of the mass transfer. Let's go to the third case at large overpotential. In case B, I have said the current is just proportional to the potential at small overpotential range. It is time to go to the large overpotential range. So I'm saying about this region for the cathodic process or this region for the anodic process. Here is the Butler-Balmer equation version 2. Of course, the overall current is the summation of the cathodic current and anodic current. Let me focus on the cathodic current in this case. I mean, I'd like to apply the very negative potential far from the equilibrium potential. Then, cathodic process is dominant over the anodic process. In this situation, we could kill the second term for the anodic process. Then right now, we could recognize that current is proportional to the exponential function of eta or potential. It is different from the linear relationship between current and potential. We should think about the exponential function. If we have no mass transfer problem, then we could kill the term in front of exponential function. Then, by taking the log function for the both sides of the reaction, both sides of equations, then natural log I per I0 is going to minus alpha NF eta, or log current is log exchange current as the y-intercept minus alpha NF as the slope with the potential. That is to say, log current is proportional to potential at high potential, I mean large overpotential, while current is just proportional to the potential at low or small overpotential. Also, when we convert this natural log to normal log, then log I is equal to log I0 minus alpha NF per 2.3 eta. Again, this is the slope and this is the y-intercept in the coordinate of log current versus overpotential. Here is the current versus overpotential, and by changing the scale of y-axis from linear to log, then finally we could obtain the new coordinate appropriate for these equations. Right now, y-axis is log current and the x-axis is still potential. In the plot of log current versus potential, the data at high overpotential are linearized. Let me say this region is Tafel region in this log plot or linear plot. I mean, Tafel region is the region at high overpotential. Let me go to the low overpotential region. The data at low overpotential around the equilibrium potential drop down abruptly in the plot of log current versus potential. Of course, in the original curve of current versus overpotential, this is the linear region. However, in the log scale for the current, this linear region is converted to the drop-down region. So, practically, we have used this plot for the data at high overpotential region or Tafel region, because we could recognize the linear line about the data at high overpotentials. In this case, the slope is, of course, this one. I mean minus alpha NF per 2.3. Also, the y-intercept is log exchange current. So it means from the y-intercept you could calculate, well, you could obtain the exchange current, and from the slope you could obtain the product of transfer coefficient of alpha and the number of electrons transferred, n. If you know the information about the number of electron transfer, then you could calculate the alpha. That is to say, we could obtain the two parameters of vertical Balmer equation, exchange current and alpha, from the experimental data by feeding the experimental data with the vertical Balmer equation at high overpotential, which is the log I is equal to log I0 minus alpha NF per 2.3 eta. Okay, so here is the real data about the current versus potential. The reaction of interest is the reduction of mangan 4 plus to mangan 3 plus on platinum electrode in 7.5 molarity of sulfuric acid. And you can find some experimental data here and there. And in the plot of log current versus potential, here, 3 different behaviors are found according to potential range. The first thing is here. At low overpotential around equilibrium potential, that is to say linear region, I have said in the previous slide, current increases linearly with potential. Therefore, current drops down abruptly in log scale, like that, in the red box. Then let's go to the Tafel region. At high overpotential range or Tafel region, current increases exponentially with potential in linear current versus potential curve. Therefore, current in log scale here is linearly proportional to potential. I'd like to introduce the third reason here in the real experimental situations. This is called diffusion limited region. At very high overpotential, more higher than the Tafel region, current is not determined by charge transfer anymore. The kinetic capability of charge transfer increases exponentially with overpotential and finally exceeds the kinetic capability of mass transfer. It means the charge transfer limited system up to the Tafel region is converted to the diffusion limited region. Therefore, the overall current is limited by potential independent diffusion process. Then, at very high overpotential, you will have the constant current, which is independent of potential. The limiting current is obtained at this region. So, as a summary, you should think about 3 different reasons about the current versus potential curve. First one is linear region, the other thing is Tafel region, and the third one is diffusion limited region. Okay, so in this case C, I have said the Tafel region are there at high overpotential before reaching the mass transfer limited situation. I'd like to introduce Tafel equation here. Eta is equal to a plus b log I. Before the Butler-Balmer equation is developed, Tafel found that the potential is just proportional to the log function of current, especially at high overpotential region. And he have presented this Tafel equation. This Tafel equation is empirical relation based on experimental data. So the Tafel parameter A and B is physically meaningless. A is the y-intercept for the curve of potential versus log current, and B is called Tafel slope. It is a very well-known parameter. Then in this graph, I have changed the log current axis into x-axis. Then the potential is the y-axis. This is so-called Tafel plot based on the Tafel equation. So eta is going to y and log I is going to x. In this case, the slope is going to b, which is the Tafel slope, and y-intercept is going to a. Of course, Tafel slope should be obtained from the Tafel region at high overpotential before reaching the mass transfer limited situation. However, at lower overpotentials, the experimental data deviates from the Tafel equations. The green line indicates Tafel equation for cathodic and anodic. I have said the Tafel equation was presented before the Butler-Balmer equation is developed. The Butler-Balmer equation is the theoretical relation between current and potential based on reaction coordinate diagram. Therefore, by comparing between the Butler-Balmer equation at high overpotential and Tafel equation, we could get the physical meaning of A and B. After converting this equation into the Tafel form, then we could describe the Tafel parameter A and B as the function of exchange current and the product of alpha, transfer coefficient, and the number of electron transfer. So A has the information about I0 and alpha n, both of them, and B has the information about alpha n. Tafel parameters A and B could be calculated by fitting experimental data like that with Tafel equation. Then from A and B, physically meaningful exchange current and the product of alpha n are calculated by using this equation. So finally, we could obtain the Butler-Balmer parameters having the exchange current and alpha values. If you know the information about the number of electrons transferred. Also, from exchange current, you could obtain the value of the standard rate constant. If you have the information about the standard rate constant K0 and the transfer coefficient alpha, then you could say I could have everything for the electrochemistry of our interest. I have said that the current versus potential curves can be split into three different regions. The first region is the linear region, at which current is just proportional to the potential. The second region is Tapfer region at relatively higher overpotential, at which the current is proportional to the exponential of potential. And in the third region, you could meet the mass transfer limited because we have a very high overpotentials applied into the system. Therefore, the charge transfer kinetics or charge transfer kinetic capability exceeds the kinetic capability of mass transfer. So the overall process can be limited by mass transfer situation. The Butler-Balmer equation could cover the first region and the second region, that is to say, the linear region and Tapfer region. However, the Butler-Balmer equation cannot cover the mass transfer limited situations because we didn't consider the effect of mass transfer to the overall current. In this slide, I'd like to generalize the Butler-Balmer equation by incorporating the mass transfer effect into the original Butler-Balmer equation. Here, Butler-Balmer equation version 2, the overall current is the cathodic current minus anodic current. Each current term have, of course, the exponential function of potential term, and also the fractional compositions are there, which is defined as the surface composition per bulk composition for the cathodic process and anodic process. We should think about this term again. In the previous derivation for some special cases of Butler-Balmer equations, we have assumed that there is no mass transfer problem, so surface concentration is going to bulk concentration. Then this fractional composition is going to 1 for the cathodic process and anodic process. In the previous chapter 3a, at which we have learned about the semi-empirical approach for the mass transfer limited systems, we have derived several equations. For example, the current per NFA, which is mole flux, is equal to mass transfer coefficient with the concentration difference between bulk and surface. The other equation is the limiting current. The limiting current is obtained at surface concentration is going to 0. It means oxidized surfaces is totally converted to reduced species for the cathodic case. Or for the anodic case, the surface concentration of reduced species is totally converted to oxidized species. So the limiting current, for example, for the cathodic process is mass transfer coefficient with bulk concentration. And then let me divide the first equation by second equation. Fractional current is 1 minus fractional composition, or fractional composition is equal to 1 minus fractional current. So let me replace the fractional composition term in the Butler-Balmer equation version 2 by the 1 minus fractional current for cathodic process and anodic process. Then we have obtained this equation. After getting together all of the current terms on the left side of the equation, then we could describe the current as a function of the overpotential. It looks really complicated. Exponential term for the cathodic process minus exponential term for anodic process, and the denominator has some exchange current term plus cathodic process minus anodic process. You don't need to memorize this equation, even if you should memorize the Butler-Balmer equation. Let me simulate the Butler-Balmer equation modified with the mass transfer effect in this graph. I have simulated it with three different conditions. X-axis is the eta, of course, and y-axis is the current normalized by limiting current. For drawing this graph, I have assumed that the limiting current for cathodic process is equal to the limiting current of anodic process for simplifying the equations. The current was normalized by the limiting current. Therefore, for all of the conditions, the curves is going to 1 for the limiting situations. Also, those three curves have obtained three different values of the current ratio of exchange current per limiting current. As you know, the exchange current is a measure of charge transfer kinetics, and limiting current as a measure of mass transfer kinetics. Therefore, the current ratio of exchange current to limiting current can be used as a measure of which process limits the overall kinetics. That is to say, if you have large values of the exchange current per limiting current, then we should go to the value at 1. This is the maximum value for the current ratio in this case. Then you could observe that mass transfer controlled region here reached earlier than the others, or here. As the values of the current ratio of exchange current to the limiting current is decreasing to 0.1 and 0.01, then charge transfer controlled region, which is the exponential function of potential, is extended more. So you can clearly observe the Butler-Balmer equation from here to there. However, if the exchange current is very higher than the limiting current, then you can observe only linear region for the Butler-Balmer equation, then go to the mass transfer limited situation. This equation is the more generalized version of Butler-Balmer equation by incorporating the mass transfer effect to the charge transfer controlled situations. That's it for the chapter 3C about the charge transfer limited systems.